Alright, silly people, here's the situation. We're going to be talking about some properties of similarity transformations. Those just being that if you have some matrix T in an orthonormal basis E, uh, then a similarity transformation would be one where you have a final matrix T in basis F, which is equal to some transformation times TE times the inverse of said transformation, right? Um, and so what if you had the matrix, which is just A, B equals C, uh, all of them in basis E. So is matrix multiplication conserved whenever you do a similarity transformation, i.e., does AF BF equals CF? Well, what we can do is we can do AF times BF because we know that it's going to be S. Let's do it like this. AF BF is going to be SAE S inverse SBE S inverse, which we know that S times S inverse is going to be the identity matrix, so we can write this instead as S A E B E S inverse, which is, we know from this equation, just going to be S C E S inverse. So that's just going to be the similarity transformation of C, so it's going to be CF. So yeah, this is a true fact. We just proved it. The next thing that Griffiths asked, that if you have some Hermitian matrix that you're applying a symmetry transformation on, so you're taking HE to HF, where it's going to be S HE S inverse, and then assuming that if S is unitary, i.e. that S dagger equals S inverse, and if HE is Hermitian, that is that HE dagger is equal to HE, then HF is also Hermitian. That is HF dagger equals HF. Right? That's what we're proving. So just taking this equation up here, the HF equals SHE S inverse, and doing the complex, or doing the Hermitian conjugate of it, so we have HF dagger equals SHE S inverse dagger. We know how taking the dagger of something like this works, right? Because if you combine the latter two matrices into a T, so we can say HE S inverse is equal to T, then we have ST dagger, which we know from a couple problems ago that this is going to be T dagger S dagger, or in other words, the Hermitian conjugate of HE S inverse times S dagger, which means that it is actually S inverse dagger, HE dagger, and S dagger. Now, we're given the fact that S is unitary, so we know that S inverse is actually equivalent to S dagger. So we can instead write this as S, and also we know that HE is equivalent to HE dagger, so this is S times HE times S inverse, right? That's one way to write it. Now I notice that all this time we were doing HF dagger, but at the end we got an expression that is exactly the same to HF. So HF dagger equals HF, and it is Hermitian for sure. Then Griffiths is going to ask, show that S carries an orthonormal basis into another orthonormal basis if and only if it is unitary. So, okay, we have a common thread here, and that is that we're starting with an orthonormal basis. So I'm going to call the transformation in that basis O, in basis E, right? And it is a orthonormal transformation. So that just means that if you take the complex conjugate of it, or the Hermitian conjugate of it, you get back its inverse, right? That is a orthonormal basis transformation, right? So that's going to be a common fact for both sides of this proof. The first side I'm going to say is that whenever we do the similarity transformation, we get back out another orthonormal basis transformation, so it's going to have the same property as this. And so running out what that similarity transformation is, we have OF equals S OE S inverse. And so over here, let's take the Hermitian adjoint of both sides. So we have S OE S inverse dagger, and then so this is S OF dagger equals, it's going to be the inverse of S, and then the Hermitian conjugate, and then also the Hermitian conjugate of S times OE, and then that's equivalent to S inverse dagger, and then it's OE dagger S dagger, right? We can also take this equation in a different direction and just take the inverse of both sides. So we have OF inverse equals SOE S inverse. So on the right hand side, that turns into S inverse inverse times the inverse of SOE. S inverse inverse is just S, and then this is going to be OE inverse times S inverse. And over here, we know that we know that the Hermitian conjugate of OE is equivalent to OE inverse. Right. So for this to work, then these two expressions have to be the same from the result, so, or from the assumption. So that means that S dagger has to be equal to S inverse. S dagger equals S inverse. And so, yeah, if you do a similarity transformation of an orthonormal linear transformation, then you get back out an orthonormal linear transformation. Sick. Now we have to prove the thing the other way around. That is that if S is unitary, that is that S dagger equals S minus 1, then the final thing, that OF dagger is equal to OF inverse. And we can do this in a very similar way. Again, by going to this equation, that OF equals SOE S inverse. Take the complex conjugate of both sides, so OF dagger is SOE S inverse dagger. Distribute that, and we get that it's S inverse dagger times SOE dagger. So it's S times OE dagger, S dagger. So it's S OE inverse, S inverse. And then again, take this in the other direction of taking the inverse of it instead. So we get this sort of action. Distribute the inversion, so it's S inverse inverse SOE inverse, so it's SOE inverse S inverse. So yeah, they are actually equal. So then OF dagger does equal OF inverse. Fun.